Welcome back for our second and final lecture on weather. So in the last lecture, we talked about the variables on which weather depends. Those variables were temperature, a measurement proportional to the average kinetic energy of the molecules, humidity, that is the measure of how much moisture is in the air, pressure, the force per unit area that is exerted by the air. And then finally, there was land and terrain considerations, whether it's over land or over sea, etc. And so we spent a lot of time talking about humidity and relative humidity. And we talked about how temperature changes as an air mass rises, and that when you have evaporation, it causes cooling. And when you have condensation, it causes heating in the air masses. And so now we're going to take that information, we're going to try to use that to learn a little bit about weather. So what we're going to cover today is about different types of clouds and how they develop, and then how storms develop from those. So let's start right off by looking at clouds. So here is an overview of clouds. You have cirrus clouds. Cirrus clouds are like wispy hair-like. So hair curls is seriously what cirrus means. And you can look at these and you see, yeah, those look like hair curls. Now, these are just drawings. We're going to look at real pictures in just a minute. And we have cumulus clouds. Cumulus clouds are the type that look kind of like puffs of cotton balls. And you have three types of cumulus. So you have, well, you see here's cumulus. And cumulus means that they're lumped. And then we have stratus. Stratus means flat layers. So let's look more specifically at clouds. Now, first of all, you have different clouds at different altitudes. So high altitude, which is mostly ice. In fact, the top ones are all ice. And this here is usually ice. Usually it can have a little bit of water. So the ones that have cirrus in them are the highest clouds, above 6 kilometers above sea level. Then the middle clouds, alto means high. So those are middle level, the ones that say high. So they're still relatively high, just not as high as the cirrus. Then the low ones are the ones that have stratus in them. Now there is a stratus here as well, but we're going to look at these more carefully. And then we have some with vertical development. They're ones that go from low to high. They extend through a range. So let's look at these more carefully. So here's a cirrus cloud. Cirrus curls of hair, like I said. They're very high. They're very wispy. They're being blown by the air currents that are up there at high elevations. These are the most common clouds, and they're composed exclusively of ice crystals. Next, we have the cirrocumulus. So you see here, yeah, that looks like the cotton ball idea. They're very high, and so they look like little tiny cotton balls. So the ones that are high with the smallest size cotton balls, those are your cirrocumulus. They signify that you have convection, that is, you have warm air rising up. And they're composed of ice crystals with just a small amount of water. Now, the cirrostratus clouds are probably one of the most interesting clouds. They're layered curls of hair is what that means. And they're really thin. So oftentimes you can't even tell they're there. You can only really tell they're there because they're the things that make these halos around, like the sun and the moon. And they're composed of ice crystals. So when you see those halos, you're seeing cirrostratus clouds. Now we get to the mid-level ones. Alto still means high. So alto cumulus means high heaps. Cumulus, so you have these cotton ball things, but now they're bigger. They're bigger, they're lower. They're larger and darker than the cirrocumulus. Remember, these are the cirrocumulus. So larger and darker. And once again, they signify convection currents. Altostratus. These are, stratus means layered, alto is high, so they're high layered. Gray or blue-gray. So they're darker in color. and they will cover most of the sky, and they look fairly featureless. So when you have just the sky is gray, all the leaves are brown, and the skies are gray, you got altostratus. Nimbo. Nimbo means rain. So nimbostratus clouds are layered clouds that are filled with water. They're going to produce rain, snow, or sleet, but no thunder and lightning. So the stratus clouds, the flat ones, they don't produce thunder and lightning. Not very, very frightening. Cumulonimbus. What did that nimbus word mean? Rain. So cumulonimbus, these are the things that are called thunderheads. These are the things that bring you the big stinking storms. You have the anvil shape up here on the top. You had a lot of upward motion. Remember, the cumulo ones, all of them have been signs of the upward motion of convection. So they tower vertically. The water vapor goes up quickly, and then it can produce lightning, tornadoes, hailstones. This is the thing that damaged our roof. We're going to have to replace the roof in our house in Lincoln because Sunday morning we had a hailstorm that damaged the roof. Cumulonimbus clouds. Now, cumulus alone. Cumulus alone is a low-level cloud. It's once again clumps. And these are the puffy things that we usually look at and say, oh, I see a ship. No, that's Snoopy. Those are cumulus clouds, what we're usually look at. They have flat bases. Flat bases because that's the level where you reach saturation, where you went from unsaturated to saturated, and suddenly you nucleate and form lots of water droplets, and then you see the cloud. And so they could be water or ice in there. Stratus clouds, featureless, right? You look out here and it's featureless, dark gray to white. So once again, this is a high fog. It's basically the same thing as a fog. It's just more than 50 feet off the ground. And the last one that I have here is stratocumulus. Stratocumulus is, okay, strato means layers. Cumulus means heap. So it's heaps and layers, large, dark, rounded masses. That's all I have on that. So those are your basic clouds. Now, clouds develop because you have condensation rate exceeding evaporation. That is, condensation is going from moisture in the air to droplets in the air. Evaporation is going from droplets in the air to moisture in the air. And notice we have above the lifting condensation level. What is that lifting condensation level? Well, let's just look back here. The lifting condensation level is the level where you reach saturation. Okay, I'm using different forms of speech. Saturated. And so that's the lifting condensation level. So as you have air rising, remember if the air is rising, as it goes up, the temperature is dropping. And if it's dry air, if it doesn't have condensation, then we have the adiabatic level of 10 degrees Celsius per kilometer. And then when it reaches that lifting condensation level, that is where it reaches saturation, now you're starting to form droplets of water in the cloud. And now as it continues to rise, now as you form droplets, that's actually generating heat because condensation generates heat. So it's warming up, so it's not cooling as quickly. And so now the temperature is dropping by 6 degrees Celsius per kilometer because now we're having the moist adiabatic lapse rate taking over. So this was dry adiabatic lapse rate. And up here, it's the moist adiabatic lapse rate. Now, the height of the cloud base, that is the height where you reach the saturation point, and how thick the cloud becomes above that depends on the environmental lapse rate. That is typically 6.5 degrees Celsius per kilometer. How quickly the air cools as you rise, just as you go through the air. Dry adiabatic lapse rate of 10 degrees Celsius per kilometer. How quickly the temperature of your air parcel cools as it rises, if it's dry air. And the moist adiabatic lapse rate, 6 degrees Celsius per kilometer, is how quickly the air cools if it's reached the saturation point. Now, looking at this picture, which of the following clouds appears at highest altitude? The picture tells you what it is, and we also went through the order. So the highest level, even though alto means high, alto is not the highest level. Stratus is actually very low. Stratus is the flat layered clouds we have down low. Nimbostratus are layered water-filled clouds that are reasonably low. And cirrus are the highest of the clouds. Now, precipitation formation. Precipitation, just like in chemistry, when we look for precipitate in our mixtures, precipitation is when we have moisture falling out of the cloud. Now, we have formation of dust here, and formation involves dust. You have in the cloud water, and then you have little dust particles. And those dust particles form nucleation centers that water will stick to. And so those little dust particles then will be the basis for starting water droplets. So those help us to form water droplets at a lower temperature. If we didn't have any of those little dust droplets in the air, then we would actually get up above 100% humidity. That is more moisture than the air can hold before we would form water droplets, and then we would have a very dramatic formation. Updrafts are important because updrafts are going to bring the air and the moisture up. They're going to result in a cooling of the cloud, and if you cool the cloud, then the dew point is going, you drop below the dew point, and you form water. Growth of stationary drops of water, falling of raindrops. Okay, so these last two are a little more obvious. The vertical development of the cloud is, talking about how it rises up and how that is going to affect everything thereafter. So here is something that you may have heard of, and you may have noticed it, but oftentimes you're not really aware of it. You hopefully know that if you look off in the distance, you see these clouds, and then you see something like this, and you're like, it's raining there. You actually see what looks like a shadow in the air, and that's the rain falling. But sometimes that shadow doesn't make it to the ground. What's happened is, as soon as the water droplets got big enough that the upward force of water droplets rising was not enough to keep them up, they started falling, and then they started evaporating. So you start with a big water droplet here, and as it drops, it's evaporating, getting smaller and smaller. Until, in this case, it evaporated completely, and so down below this point, you no longer have droplets. You just have the humidity was increased by this. And so this is called virga, when you have a cloud that is dropping water droplets, but those water droplets disappear before they reach the ground. And it's because of the evaporation of those water droplets once they leave the cloud. Now, air masses are what control our weather. And so the air masses have 6 categories. You have the first lowercase letter is M for maritime. In other words, over water, over ocean, I'll put. You have C for continental, over continent. And then you have, that's all for that. I thought it was 3, but it's only 2. So you have those 2 for the first letter. And then for the last letter, the second letter, you have A for Arctic. The second letter is capitalized. P for polar. And I'll be honest, in my mind, polar and Arctic mean roughly the same thing. Arctic means north of the Arctic Circle, but that is the polar region. And then finally, we have T for tropical. So Arctic is the farthest north, polar is the middle, and tropical is near the equator. And so we have, if you put those together, 2 of these, 3 of these, that gives you 2 times 3 equals 6 options. And so you have the maritime Arctic, that is Arctic over water. And so it's cold because it's Arctic. It's moist because it's over water. Unstable. That's kind of an important thing to note. And then continental Arctic, like Greenland, right? That's a continent, or it's a landmass, but it's not tropical. And so it's still cold, but it's dry because it wasn't over water. And because it's dry, it's stable. Then we get to the maritime polar. So this is like North Atlantic and Pacific Oceans. It's not up in the Arctic Ocean, but it's not tropical. It's in between. So over water, cold or cool. I said that wrong. Over water is moist. The temperature is cool because it's farther away from the pole. And because it's moist, it's unstable. And then continental polar, that's like over Canada and Siberia. And so that's obviously cold, even though it's, polar and polar here. Over land is colder because the sea helps to moderate things. Because it's not over water, it's dry, which makes it stable. And then finally we get to the tropical ones, maritime tropical, warm because it's tropical, moist because it's over water, and once again, unstable because of that water content. And the final one, continental tropical, that's hot, not over the water. Notice if it's continental, it starts as cold in Arctic, stays cold for polar, and then is hot in tropical because you don't have the water to moderate temperatures. If you're over water, if you're maritime, then it goes cool, and cold, and warm, excuse me. So it's not as extreme over the water. Dry air over the continents, stable aloft, but unstable at the surface. So even though it's dry, it can still be unstable at the surface. So these different types of air, different temperatures and moisture content, are what drives our weather patterns. So here's just pictorial showing where we expect to see these different types of air masses. Now, air masses and fronts, basically the lifting of an air mass that contains moisture is what's going to cause a lot of our clouds and what we see as weather patterns. So there's 3 types of lifting. You have convectional lifting. When we studied heat, we had 3 forms of heat. We had conduction, that was direct contact. We had radiation, which was electromagnetic waves, like light. And then we had convection, which was an intermediary fluid carrying the heat. And so convectional lifting is you heat the air, but the hot air expands. And because the hot air expands, it's less dense. And because it's less dense, it floats up on more dense air. And so convectional lifting is what caused those cumulus clouds. Remember, cumulus for each one I said, it's a sign of convection, convective lifting. Now, orthographic lifting is when you have land features that are causing the air to rise. And we'll see example pictures coming up. And then frontal lifting, that's air is causing it to rise. So we'll look at each one of these and see how they play into forming clouds and rain. So convectional lifting gives you your cumulus clouds. So here we had moisture. Now, this is a dry area, so there wasn't much moisture in the air. But down here near the surface, the ground absorbs a lot of the sunlight, gets hot, heats the air, and then that hot air rises up. When it reaches the level of saturation, it forms clouds. So you see these clouds. It's hard to tell in the picture, but the clouds are all at roughly the same level because that's where you reach the saturation point and they form clouds. And then how high they went above that depended on how much temperature difference you had to raise them and how much moisture content you had. Orthographic lifting, you might remember from the last lecture when I talked about Chinook winds. Well, that was an example actually of orthographic lifting. If I have air that is forced up a mountain, it's lifted because of the terrain. And of course, because you had that air lifted, it cooled as it rose. And so you reach the level where you're at saturation and water droplets form, and then it rains on this side of the mountain. And then that air is now cool at the top, but it's dry, and it comes down, giving you a warm, dry air. So this rain shadow region, it's a region where you very, very rarely have rain because all the moisture is dropped on the other side. And so this side here could be green and lush. And this side here is desert-like, arid. So that's orthographic lifting. And finally, and really most interesting, especially if you're in Nebraska where we don't have any mountains, is frontal lifting. So frontal lifting is when we have a warm air and a cold air mass meet. And so there's two ways, well, there's more than two, but there's two ways I focus on. A cold front is when we have a moving cold air mass. So this is cold air on this side. This is warm air on this side. And it's the cold air that's moving to make it a cold front. So the word before front tells you which one's moving. Now that cold front meets the warm air. And just like when we talked about plate tectonics and we have the more dense oceanic plate subducts or slides underneath the less dense continental plate, we have the same thing here. The more dense cold air pushes its way underneath the less dense warm air. And so the warm air is forced up on top of the cold air. But of course, as that warm air rises, then its temperature drops. And as the temperature drops, it is going to then form water vapor. And this is how you form cumulonimbus clouds. Remember, nimbus means you're going to have rain from it. Cumulo means clumpy. So those cumulonimbus clouds are formed when you have a cold air mass rushing into a warm air mass. So that's a cold front. Of course, the opposite of a cold front is going to be, I think you can probably guess this, a warm front. So a warm front is when you have warm air that is coming and rushing over a cool or cold air mass. And so once again, just like with continental plates, the less dense thing goes up on the more dense thing. And so the warm air rises. But notice it's a different type of cloud here. You have a nimbostratus cloud that drops rain, but no thunderbolts and lightning. Whereas with the cold front, you had thunderbolts and lightning. You had the cumulonimbus or a thunderhead. Whereas when it's the warm front that comes in, you just have a rain. And I didn't point out, here that, you do move further up. So you have the cirrus clouds up high. Here, you can see the progression. You form nimbostratus and it rains, and then it keeps pushing up and you have stratus, layered clouds. Altostratus, high layer clouds. Cirrostratus are the wispy layered clouds, and eventually just the cirrus, the very wispy. So those are what form over the cold mass when you have a warm air mass that's pushing in on, encroaching on it, what we call a warm front. Now, the final of the types of fronts I'm going to talk about is one that is honestly confusing, the occluded front. The occluded front, if you look over in this picture, you see you have cool air that's moving to the right and cold air that's moving to the right at a faster rate. And so it's kind of like a pincher action where you're squeezing the warm air. So the warm air on this side is going up, making your Your nimbostratus type clouds here, as we saw with the warm front, and making your cumulonimbus, otherwise known as thunderheads, on the other side. So the nimbostratus drops some rain. The thunderheads have rain, thunderbolts, and lightning. And of course, if that cold air is going faster than the cool air, it kind of pinches off. And so that's what we call an occluded front, when you have the cold air meets the cool air and pushes the warm air up. So the warm air isn't even touching the earth anymore. It's all pushed up high in the sky. And so you have your storm there where the two cold fronts are meeting and pushing the warm air up. And so that's what the occluded front is. And this picture over here is actually showing the generation of such a front. So you have the cold air rushing down here. Here's the warm air, and then cool air on the other side. And yeah, I'm not asking you to understand how to read these. You probably can figure out a warm front has those little red circles, half circles, whereas the cold front has the little blue triangles. And the circles or triangles are on the side that's moving toward. But I'm not going to ask you actual questions on how to read that. The last slide in this lecture has a whole bunch of symbols on it, and we are not going to try to learn those symbols. Now, cyclones. Talking about storms, cyclonic storms are storms that twist. And cyclonic storms, it's really useful to note that in the northern hemisphere, they appear counterclockwise as viewed from above. But in the southern hemisphere, they're clockwise. They're just the opposite. And this is the result of the Coriolis effect. The Coriolis effect is the effect that because the radius from the axis of the Earth's rotation to the surface of the Earth is smaller as you move toward the poles and bigger as you move toward the equator, then the actual direction or speed that a point on the Earth is traveling toward the east is fastest at the equator and slowest at the pole. And because of that, if you were to, for instance, throw a rock north from the equator, the rock would be traveling east at the speed you're traveling at the equator. And as it goes north, the ground underneath isn't traveling east as fast. And so as viewed on the Earth, it would appear to veer toward the east. So if this is the equator, this is north, that's north, south, east, west. And the opposite holds true. If you were to throw something in the northern hemisphere toward the equator, it would deviate that way. And so the result of that deviation is what makes the cyclonic storm, so that ultimately you're going to have air rotating here in a counterclockwise direction because of the air rushing toward the center. Why would the air rush toward the center? Well, the cyclonic storm starts, well, I got a question before that. What's the name for a front that occurs when a cold front and a warm front merge? Okay, so this wording probably doesn't match the way I described it. A cold front and a warm front merge. The way I described it was when you had a cold front, and here's the warm front, and then here's a cool here. That's what this is talking about. The merging is when you force the warm in between the two, and that's the occluded. Actually, you know what? I think the answer to this was supposed to be stationary, because when they actually merge and they're not moving, it's stationary. I just prepared this beforehand, and I go lame. Violent weather. I love violent weather. My wife likes to say, I love weather. Well, I love violent weather. I also love clear weather, but I like to see storms, except for when it damages the roof of my house and I have to pay money. Or damages my car and I have to pay money. So storms are violent and rapid changes in the weather. And you have three types that we're going to talk about here. Thunderstorms, thunderbolts and lightning, lots of rain. Tornadoes, those are cyclonic storms that occur over land. And hurricanes are over water. So let's just look at these a little bit. Thunderstorms begin with humid air rising. If you don't have moist air, you don't get a thunderstorm, right? You're not going to get blood out of a turnip. You're not going to get rain out of dry air. You have to have humid air. And then when that humid air rises, it cools. And because it cools, water condenses. And that water condensation is what then leads to the storm. And if it's fed by an unstable, moist air, it can grow really big into a thundercloud, a thunderhead, a cumulonimbus. And these kinds of storms have great energy. Now, all thunderstorms include thunder and lightning. And I have to go through this because it's good physics. In this cumulonimbus thunderhead, you have up at the top ice crystals. But at the bottom, you have water. And you have little droplets that are falling through this. Actually, I want to choose a different color. Black will be my water droplets. The water droplets are falling through. And as they fall through, they're rubbing on each other and they rub charge off, just like when we rubbed the balloons and we were able to stick them to the wall. And what happens is the top of the cloud becomes positively charged. The place where you have the ice crystals is positively charged. The place that is missing the ice crystals is mostly water, becomes negatively charged. And so you have a big charge separation in these thunderheads. And that will cause you to have arcs. Now, if we look at the ground down here, this negative charge is going to push negative charges down below the surface. And so you're going to build up a positive charge at the surface. So you also have voltage difference between the bottom of the cloud and the earth. So you can have lightning, electric charge, that's going to be electrons that come down here to hit the earth. Or you can have lightning that goes up through the cloud. And it's roughly 85% of your lightning bolts are going through the cloud, or possibly going from one cloud to another cloud here. So you could have lightning strikes that are going like that. Actually, I should have made this cloud like that, and then my lightning strikes could be going like this. So like 85% of your lightning strikes are between clouds, and only about 15% actually strike the ground. So when we have thunderstorms there in Lincoln, I love to sit there and look at how close is the lightning, how many lightning strikes do we have in the last 30 minutes. I have a nice little app that tells me that. But I have to remember that most of those lightning strikes were in the clouds. They didn't hit the earth. And they monitor these by looking at the electromagnetic pulses that are generated when you have a lightning strike. Because when lightning strikes, you are going to send out a very strong electromagnetic wave. But then you also have another thing. You're putting a lot of energy through here, so the air around here heats up. And that hot air expands, and that rapidly expanding hot air is what makes the thunder. So the thunder is just very rapidly expanding air, making a high pressure pulse that we hear as the thunder. Now there's one more thing that I want to talk about with this. You have this thunderhead, and the thunderhead might extend, 5-10 miles out in front of the storm. So the storm is moving this way, and you have 5-10 miles out here, and that's all positive charge up there. And so sometimes you will have a clear skies. Once again, lightning is in red. A clear skies lightning strike. Now, in this case, that was positive, and so the ground here is going to be negative, being negative being attracted to the positive. And this here, it had to travel a much bigger distance than this did. Because it had to travel a much bigger distance, you needed a much bigger voltage difference, and thus this is a much higher energy. If you get struck by lightning in clear skies, you're almost certainly going to die because of this higher energy lightning strike. If you get struck by lightning underneath the storm, there is still a good chance of death, but there's also a reasonable chance of survival. You might know that one of our IRR teachers a few years back, Aaron Kent, on an IRR field outing, was actually struck by lightning, and he survived, thankfully. So that would be the kind of lightning where you have the storm down low where you survive. Tornadoes. I have to tell you, graduation weekend last year, I think it was after graduation, Amy and I went to walk around Holmes Lake, and a storm developed very quickly. And about the time that we were at the dock area, the tornado sirens went off. Now, when the tornado sirens go off, that means that a funnel cloud has been seen. I don't think it means that it's hit the ground. I think there's a funnel cloud that's been seen. And there was a tornado that touched down not close to us, thankfully, at the edges of town while we were out there walking. So we're hearing this, tornado siren and getting a little bit edgy. But, I told you, Amy said she loves weather. She loves this kind of violent weather, and so do I. And so we're out there walking as quickly as we can to try to get home. And up above us, we had a rotating funnel cloud. And I'm like, oh no. And Amy's like, oh, let's walk back and look up. No, honey, no, we probably shouldn't. We should go home. And so we kept going, and pretty soon the hail hit us, very hard hail and rain. We went running home. I don't know if I've ever been so soaked in my life except for when I was swimming. So don't do that. There's danger. Could have been struck by lightning. Hail is actually not all that safe, as you probably know. So tornadoes, a funnel-shaped column of air rotating around a low-pressure core. Now, what makes that low-pressure core? Well, remember, the cumulonimbus has as its core hot air, hot, moist air that rises. So that hot, moist air is rising. And since it's rising, it's vacating the premises, leaving behind a low-pressure region. And because that's low pressure, then more air rushes in because you go from high pressure to low pressure. So you have that low pressure rushes in because of the Coriolis effect. It swirls around, and you maintain that low pressure where air is going up in the center. And that's how you form a tornado. Now, it's called a funnel cloud if it doesn't hit the ground. So Amy and I were not under a tornado. We were under a funnel cloud. Still dumb stuff, okay? Tornadoes are obviously dangerous. Just this week, there were tornadoes again in Tennessee, very close to Southern. Did a lot of damage. And they're dangerous because it says here suction. Well, let's not say suction. Let's say low pressure. It's low pressure. Change to blue. There we go. Low pressure. And because of the low pressure, high pressure pushes in. Right? You can't truly suck. You just have low pressure, and then high pressure pushes in on the low pressure. And it'll create, like, you have your house and you have the air blowing over it. And so because of the Bernoulli relations, you have low pressure here, and underneath the roof, you have your normal atmospheric pressure, which we're going to call high pressure here. And so it pushes it up. Or you could just have those fast winds hitting the side and knocking it over. So I'm sure you've seen pictures of those poor folk in Tennessee whose houses were knocked down because of those winds battering their homes. Now, Tornadoes and hurricanes are different because tornadoes are over land, hurricanes are over sea. And hurricanes are our most exciting, most energetic storms on Earth. And so hurricanes occur over water. Their energy comes from the heat release from condensing water vapor. And it starts with warm ocean water. You have warm ocean water, which creates a warm, humid air above it. That would be maritime tropical, right? Maritime because it's over ocean, tropical because you have to have warm. So they start in maritime tropical situations, and that warm ocean causes warm air above it. That warm air expands and rises up. And so it starts with a low pressure system. So you might hear people talking about a tropical depression. Tropical depression is where you have a low pressure system over the ocean because of warm water in the ocean. But just like with the tornado, that rising warm air then, leaving behind the low pressure, air rushes in, Coriolis effect makes it spin, and you have the same fundamental thing that caused the hurricane. But you have a lot more energy feeding it from the ocean's warm water, and so you develop much bigger, stronger storms from that. So you have that, as it says here, continuous supply of energy from tropical waters. You cool that water, you're going to kill it right off. And so if it comes over land, well, you no longer have the warm water and it dies. So now hurricanes, obviously, they don't dissipate instantly, so they will extend a little bit inland, but they die off quickly as they go inland because they no longer have the warm water feeding them. If you look in the textbook, it has a lot of information talking about the eye of the hurricane. You have the upward air creating a higher pressure on top, and it makes it actually kind of clear and stable in the eye of the hurricane, with the storm all around and all of your lightning and rain dropping outside of the eye, but near to the eye, near to the center. I didn't put that in my lecture, but just something to mention here. Hurricanes have winds up to 300 kilometers per hour. 300 kilometers per hour. That's like 200 miles an hour wind. That's really extensive. You know, here at my house in Colorado, we have winds that might be 100 miles an hour. Now, that's half of what you get in a hurricane. It's still pretty amazing, let's be honest. Okay, so another question to make sure you've followed along as we've gone through our weather lecture here. We're almost to the end. What is the eye of a hurricane? And I'm sure you don't know the song by R.E.M. It's the end of the world. No, Eye of the Hurricane. Listen to the world. The eye of the hurricane is, you have this big hurricane, and the eye is the center where you actually will have clear skies and sunshine. And you're like, ooh, the storm is gone. But actually, the storm is raging all around you, and you're just in that center calm. Now, it's high pressure up here, but on the surface of the earth, it's low pressure. So we're going to call it the low pressure region because you're on the surface of the earth, you're not up above. And it has lowest precipitation, but probably no precipitation. And where the upper level air descends, no, it's where the lower level air rises up. So, weather forecasting. Are you going to be able to forecast weather based on this lecture? If you can, you're doing better than me. But it involves collecting data from all over the world. You have to know what's happening hundreds and maybe even thousands of miles away so you can see how all of that air is going to interact and how it's going to affect you in 3 days. So computers analyze the data. Now, a human can make predictions over a short term. Longer term predictions, we all know they're crazy unreliable because it's such a complicated system. So we're constantly working to improve our understanding, improve our ability to predict weather. But in a place like Lincoln, we always laugh. Oh, it says in 2 days we're going to have this weather. Well, that's at least a 50-50. And this is our final slide. Weather maps. All kinds of symbols that we aren't going to learn, but just so you can have something to say, these are what things look, like the cold front. We talked about that with the yellow triangles, the warm front with the red circles. Stationary front has opposite directions. Remember, the direction it's traveling is the direction it has the symbols. So the stationary front, both directions, it's not traveling. Occluded. Okay, so we talked about some of these things. Obviously, there's many things we didn't talk about. This is a standardized way of indicating weather conditions. The flag here tells you about the wind speed and its direction is given down below. Somebody who's really into the weather can look at these and they can figure out a lot of things by looking at that map. We are not there. All right. I hope you feel a little more knowledgeable about weather, not able to predict it, but able to identify, ooh, look, that's the kind of cloud that might bring rain, or that's not going to bring rain. All right. Have a great day. See you next week.